Hi guys. So in the series of master class in generative AI, especially in ML, today I'm going to share you a video which is very well described video for the transformer. Attention, all you need, right? And this video is basically going to give you a good sense of understanding about the transformers. So please listen.
You've heard a great talk just before about how to use neural networks to translate. And this has been quite a big thing in all of natural language processing. So people have been doing a lot of stuff in natural language processing, parsing, translation, finding entities, anything towards making machines understand text a little bit. And then came these neural networks, and as you've seen in the previous talk, the main thing is they generate the next word. Right? They look at the past, maybe have some recurrent neural networks, maybe some other mechanism, and the thing they're trained on is to generate the next word of the output. And mostly for the last year and a half or 2 years, which is like distant past in deep learning, prehistorically, it's been done with RNNs. So you have this LSTM cell, it generates the next word. And when I started looking at it, I didn't believe that you can train something that will translate from English to German from raw data with such a generic model. I mean, you've seen the talk, the previous talk, and all the kinds of mistakes it does, and the phrase-based and non-phrase-based systems. But to me, I'm not sure if you got this vibe that this is something incredibly amazing because it's a generic system. It's 4 lines of equations, and you give it data. And it learns to translate, it learns to speak fluent French and actually on context from English, right? But this has been done. So what's missing? Well, the translations you saw, they have some problems, some mistakes, and we were thinking for a long time, like what's the gist of this problem? What is not so great about it? And it turns out these neural networks, you translate sentence by sentence. You do it like on the level of tokens or words. So a sentence maybe has 40 words, a long one maybe has 60. But when we speak, we think about context that goes way beyond that, right? When I speak, when I go to see my old friend, I will start talking to him about things we talked about 20 years ago, maybe, and I'll know it. I'll immediately recall what's needed there. And this thing, which people call different names, maybe long-range dependencies or long hop gradients, it seems to be like one really important thing to solve and to tackle to make these networks like understand more. And so if we train the network with a long range, with something that can really look back many thousands of steps and remember it, well, we could train a translation, but translation is usually sentence to sentence. And I'll tell you the details about this model in a moment. But imagine if we just trained it to generate text, to write something. And since we want it to be longer range, let's say we train it on Wikipedia articles. Okay? So that's called a language model, something that just generates the next word. Since it's a model, it's probabilistic. So it's a probability distribution over various articles. But we trained one. And this is what it generates. So the only thing it's conditioned on is the title, which is the transformer, because that's the name of our model. So let's see, the transformer are a Japanese hardcore punk band. And it's trained on markup, so it generates markup too. And then it goes on. In the early years, the band was formed in '68 during the height of Japanese music history. Among the legendary Japanese composers of Japanese lyrics, they prominently exemplified Mohoro Oda's especially tasty lyrics and psychedelic intention. I don't know what the creative part here thinks of this, but it starts as a Japanese band, then it goes on, and it generates history born from the heavy metal revolution. In 1977, well, it kind of goes off in the things, and let's go on. They generally played around Japan, growing from the top 40 standard, and then in '81, the bassist Michio Kono and the members of the original lineup emerged. Right? The interesting part is it makes up some names, and then we went to Wikipedia and checked. These people don't exist. Neither does this band or anything like this. It's all totally made up. And But it makes up this bassist, and then he is the original founder, and then there is Niji Fukuna, and you can see that since it decided it's a Japanese band, it has kind of Japanese sounding names, and it knows that the band should have a history and so on. It goes on, and then there is the band to split, right? Then in 2006, the band split up, and the remaining members reformed under the name Star Mirror, with Kono in tears. So this is totally made up by a language model. And, well, but this is not a hand-picked example. It's just sampled from a distribution. You sample again, and you have another thing. The Transformer is a book by British Illuminatist Herman Weirhead, set in a post-apocalyptic world that border on a mysterious alien known as the Transformer planet. Well, which have a different name. And you see, it knows the book has a summary, and then the book covers the world of binoculars from around the Earth, and so on, and conceptual, the Transformer universe. Principles, a setting man named the Super Congo planet, who's a naturalistic device. I don't know, sometimes it gets too strange. But what's interesting, it makes a quote from the book. It actually learned that inside Wikipedia pages about books, you have quotes from the book, so it makes a quote. And a man called Dick Lantani-Berto, known as the greatest radio, whatever. It's a strange thing. So this was a model that was trained only for like 2 days on 8 GPUs. We have better models now, and it's very interesting. The better models, they like learn to make up poems in the middle of articles about lyrics, and they keep consistency. If it's a Japanese band, it keeps talking with Japanese names about Japan. It refers to the members. It refers to the years that were there before. So, I want to give you the feeling that this is something exciting. This is not something computers were able to do like a few years ago. Yes?
The coherence of the article is because the data is homogeneous, or because he somehow remembers what he...
It remembers what it generated before.
It's
yes.
not because the data is...
Well, the data are full Wikipedia articles, so they are coherent, and it learns from that. It learns that...
So, for example, all the Japanese band articles, old articles, so...
It isn't a selected data set of just metal.
No, it's trained on all English Wikipedia, all of English Wikipedia. And so, how does it work? So you heard about RNNs, but RNNs have this problem that if you try to generate 2,000 words, the state and the gating in the LSTM would start to make the gradient vanish. It's called long short-term memory, but it's not that long. So people started to try to solve this with convolutions. That was like last year. When you take a long sequence and you make convolutions and convolutions, you can get I think that's easier to see on the picture. So if you make an RNN, it needs to go like one word at a time. So to get to here, you need to see maybe the 1,000 words before, right? Then came this model from DeepMind called WaveNet, and then for translation it was called ByteNet, but it's all the same thing, which is we make a convolution on the lower layer to jump two steps. And then the next layer skips one at every point. So it skips one here and skips one there. So in the second layers you see 4, right? The next layer skips 2 or 3, so you see 8. So for a logarithmic path, you'll get to this word with logarithmic number of layers gets to see a context. So it's much better. It's not linear like with an RNN. It's logarithmic. And they had some success translating with this. It was not bad. But it still has, it's very positional. Every layer looks like this guy sees the word number 13 before me. Why is word number 13 before me important? Maybe in this sentence it's number 12. It seems like this scheme is referencing things very much by position, while referencing by content would be a much more natural thing. So how do you reference by content? Well, there is this mechanism called attention that was introduced already with LSTMs, but we'll just look at one thing. And attention is something where you make a query with a vector, and then you basically look at similar things in your past. So while convolutions are quite a positional thing, that's why you have a different color for every position, attention looks at everything, but gets things that are similar. So maybe this guy is very similar to what I'm looking for, and this one is not at all. That's the general idea. So when you retrieve similar things, you can look at a very long context. And so imagine you're producing the name of the band member, right? Now you can attend however many steps behind. You can see, oh, earlier I said it was Michio Kono. Let me say this again, right? And with CNNs, you could do this, but you'd need to know the exact position. You'd need to compress the data very much. With attention, since it's content-based querying, you can do this quickly. So, okay, so there are attentions. What I showed you is a language model, meaning it just decodes. It has no inputs. But for translation, you need an input. So you need an attention that's from the output attends to the input. You need an attention in the input, which can attend everywhere, and an attention in the output, which only attends to things before. Now, can anyone tell me what time it is?
It's 12:18.
Okay. So I have, when am I supposed to stop? So
You can go.
I can go. Okay. So let's look at the details of the model. We have some inputs. It's, say, the English sentence, right? And then there'll be a multi-head attention. I'll go into detail of what that is later. Then there'll be a feed-forward layer. Just every word will be processed. And that's the processing of the input. Now, when we start generating output, we need this masked attention, which is like the one here. Now, I'm not sure if this is doing justice to that idea. So in a recurrent neural network, it's very clear that you go from one word to the next, right? If you, in the more standard attention things that have been there for a while, you attend to everything there and back. But if you wanted to make a language model, you cannot do this, because at the end, you're predicting the output. So from this word, you're predicting the next, meaning this word. If it could just attend to it, it will look at it and copy, but there will be no way to decode. So this would be a model that, well, it would train immediately, but had no way of inference. You could never generate anything. The trick is you want to attend to only things before you. So how would you do this? In an RNN, you can do it, but it takes you every step, every word that comes in, you process it in one step. Meaning if you have 2,000 words, you need to make 2,000 consecutive steps, which is a lot. And it takes a lot of time. It will take you months to train, and you'll not be too happy. Now, in our model, which is gone, looks at what should it stand for. There is always another head that whatever word it is in, it looks at the head noun of the sentence or the head verb. It just wants to know what are we talking about here. And it's really funny. The bigger you make the model, the more data you have, the more interesting things you start seeing with these attention heads. And okay, so that's the transformer model. And then another project was to think, okay, so it does very well on translation. It produces nice language. Can we do multitasking with this? Could we do a lot of things in common? Because it's fun to generate language, but it would be even better. Well, we need to train one model for translation, one model for parsing, one model for entity resolution, one model for grammar correction. It becomes boring at some point. It's like, couldn't we just train one model? So we started thinking in this way, and then we thought, okay, if it's one model, then it also should do images and speech. But then, how do you put an image together with a text? Well, the image is a 299 by 299 pixels, and the text has these tokens and stuff. So we didn't, it didn't seem like you can just put them together in one place. So we made these small things which we call modalities. In our model, you have the outputs. They come in, and then there is the masked attention, which is a single matrix multiply with a mask. So all of these things, they're done in parallel. You have 1,000 words. They come as one tensor that's 1,000 by something long. And then every word I needs to attend to all words before it, which will be done by multiplying everyone with everyone and masking out half of this with zeros. So this step, which does attention for maybe 2,000 words with 2,000 words, everyone to everyone, is a single matrix multiply. And the GPU hardware is extremely optimized for large matrix multiplies. So this can happen in a very quick time. And then you do this again, but then multiply with this. Okay, have a feed forward, and then do a prediction. In the sense of neural network architecture, this is a very simple few-layer feed-forward architecture. In a way, it's much simpler than the RNN. It has no recurrence. There is no weight sharing. Everything happens in a bunch of masked matrix multiplies. So what is exactly this attention? So we define attention. There is a query that will be a vector. And then there is this key and value matrix, which is your memory. So you can think like this is the current word, what I'm operating on, and this is all the past, all the words I've generated before. And keys and values can be the same thing, but they don't have to. That's why we write it like this. So what you want to do in attention is take the query, find the most similar key. As I told you, it's a similarity thing. And then get the values that correspond to these similar keys. But of course, it's soft. It all needs to be differentiable. So how to do this efficiently? Well, you take the query, multiply it by the transposed keys. So that's a matrix multiply. Then you take a softmax, which is like this exponentiation and normalization. And that gives you a mask. That gives you a probability distribution over keys, which is peaked at the ones that are similar to the query. And then this mask, you make a matrix multiply with the values, which is the same as summing over values multiplied by this mask. And there you are. You've retrieved what you want. You've done 2 matrix multiply and 1 softmax operation, which is very fast. And actually, you need to normalize it a little bit to train well, but that's a technical detail. And that's it. So how costly is it actually? Well, if you have a recurrent neural network, let's look at that first. You need to make n steps. Every word needs to make a step. And in every step, you have this dimension by dimension operation, maybe a bunch of them, but generally it's d squared when d is your hidden dimension of the network. Attention is a little scary because it has this n squared thing. Everyone is attending to everyone before it. So that's very scary, and it's scared me for a while. I was telling her maybe we shouldn't get into it. It's n squared, and then, if you do any theory, you'd say, oh, that must be worse than this. But then, luckily at Google, there is this guy Noam, and he never got his bachelor, but he wrote most of these papers. And he says, well, D is usually at least 1,000 in our large networks, while N is the number of words in a sentence, so that's like 70. So what are you talking about? This is 70 times 1,000 squared. This is 70 squared times 1,000. You're totally wrong. In most cases, this is smaller. And when we get to more than 2,000 words, we can find out ways to do more smarter things. Let's first do that. So we did it. And so one problem with attention, since it's just a similarity measure, it works as if this was just a set of words. It has no idea that this word comes after this because it just retrieves the most similar ones. But it's really important. The order of words is not arbitrary. You cannot just reorder and hope that it will translate well or generate the right next word. You need to add some timing signal, and you need to add a little bit of the positional things. So we have a multi-head attention with positional signals. I will not go into the details of how this is done. So there'll be multiple attention heads looking at different words, and they know the positions. Okay. So we'll have better pictures in a moment. Right. So we built this model. It has multiple layers of these attentions. And as is standard now, we trained it on translation. And then deep learning is a trade, right? You need to do all the tricks to make things work actually well. So you need to have dropouts in the right places. You need to use the Adam optimizer and maybe think a little bit about your learning rates and how to decay them. We use something called label smoothing in the softmax, and then when you start actually decoding from this model, you need to pay some attention to what you're doing. So there is a bunch of technical items that we did, and then that was, I think, the 5th time I did them. And then we also started thinking, well, it's actually quite tricky to do them all right. And since this was my 5th time, and also I did it with other people, I realized that the previous 4 times I always had some bugs. And then we thought, okay, so if someone from outside of Google Brain, where you likely have, like 20 people who've been doing this for longer than almost anyone else, and they can tell you what you're doing wrong, it's very hard to do this right on your own. So we decided to make a library where you could at least look at the code and get these things right. And I'll talk a little bit later about how this library came out. But then we started doing this machine translation thing. And I don't know if you got this blue from the previous talk. So there were like these phrase-based systems, and on this quite standard English-German things, they got like 20.6 blue or something like this. And then came the so this was the Google production paper, it got 24. Then there was a very recent Facebook paper that used convolutional things, it was 25. There was a mixture of experts layer paper, which is this model with some extensions, it got 26. So this was considered very high. Like if you give this to human translators, they will get something around 30. So this is kind of pushing, and of course, blue is a bad metric. Like you can get 30 with something that still makes totally stupid mistakes, and these networks are by no means perfect. But in terms of this metric, this seemed quite high. So people said, yeah, you're doing another architecture for translation. What can you get? You'll get 26.5, should be very happy. So we were, and then there were ensembles, and you see they get like 26.4. And then we were extremely happy because we trained this big transformer model, and it got like 28.4. And that's a very high number. And we looked at these sentences, and they were really better. Like they're reordered in a better way. The words come in a better position, and well, like we tested what parts of the architecture matter most. But here is a funny thing. So who knows about the Vinograd schema? So Vinograd was the scientist, and he was thinking, what's a good challenge for AI that would have to do with language? And then he thought, well, there are these things where you really need to understand the meaning of the words. Let's say I tell you, he didn't put a trophy into the suitcase because it was too small. What was too small? Right? The suitcase. And if I say because it was too big, it was the trophy. Now, okay, this is obvious to everyone. No human will ever make a mistake. When you translate it into French, and also into German, trophy and suitcase have a different gender. There is simply no way you can translate these two sentences correctly without having quite a deep understanding of what's happening in the world. And it's totally not clear how a neural network would be able to get an understanding like this. And indeed, if you try a few Vinograd schema sentences, there were no machine translation models that did any good on them. Not Google Translate, not the LSTM models, not phrase-based translation by any means. So we threw them at our new model, not expecting too much, and then it started doing some interesting things. It doesn't get them all, but this is a shorter version. The animal didn't cross the street because it was too tired or because it was too wide. You see the same pattern. And then because there are these attention heads, so when it's producing the word it, we can check where, so there are like 40 of these attention heads. The blue one is just one. And it looks at the animal and street. So this is the attention mask, the query multiplied by key, and the stronger color means that it's the bigger strength. So you can see that it looks at animal and street, and here it focuses on animal more. while here, it also looks at them both and focuses on street more. Now, it will not get everything right, but what this shows you is that this model has the capacity of thinking about relations, because it can retrieve these two things, and in the next layer start processing this to decide what to output next. So here is a bunch of this Vinograd schema sentences, and Google Translate gets one or the other wrong, while we get, like, these two we get correct, these two, this we get wrong. Well, I think it's a very interesting thing with these attention heads, that some of them you can actually interpret. You can see, like, this head, it always looks, when it produces pronouns, it looks at things that it basically